Hey guys, welcome to this video on irrational numbers. I spoke a little bit last video about what an irrational number, or mentioned the idea of irrational numbers. In this video, we're going to go through what is an irrational number, give you guys a definition for it, and also talk about how it can prove that a number is irrational or not. So let's get started. First of all, we've got our definition here of an irrational number being a real number which cannot be written in the form of a divided by b, where a and b are integers. We know that if it can be written in the form of a over b, that means it's a rational number. So now we're talking irrational numbers. If I mentioned last video again, root 2 has been an irrational number. If we plug it into a calculator, it just goes on and on and on and on forever. So a thing we could talk about with irrational numbers as sort of a generic thing is that irrational numbers go on forever, which means they don't have a terminating decimal, and they're also not a recurring decimal. It might have a couple of numbers where it does repeat, but over the grand scheme of things, it doesn't have recurring decimals. Let's look at how we can prove that root 2 is irrational. So, proof of root 2 So, how are we going to start this? What we're going to do is use a thing that's a proof, and something you guys may not have come across before, as proof by contradiction. What that means, we're going to assume for a moment that root 2 is rational. So that means that the square root of 2 is going to equal a over b for some positive integers a and b, and obviously b is not going to equal 0. We're going to assume this fraction has been written in the lowest terms, so there's no more common factors. So what we mean by that is that it's been written, say, 1 over 3, or 2 over 5, not being written as something like 2 over 6, because 2 over 6 can be taken down into its lower common factors of 1 over 3, or it's just equal to 1 over 3. What we're going to do, we're going to square both sides here. So we're going to have 2 being equal to a squared over b squared. Now, you remember from your index laws that if we square a fraction, we're squaring the top number and the bottom number. That means that a squared has to equal 2b squared. So if a is even, that means b also has to be even. Make sense? If we want to then assume for a moment that a is going to equal 2k for some value of k that's a positive integer, so for some k, let's fix that up. K being a set of a positive integer, and that's meant to be that double struct k. I'm not good at, not meant to be a double struct k, it's meant to be a double struct z. And the plus means that it's a positive integer. So we're going to substitute that into here. So we've got 2k all squared, which we know is just going to be equal to 4k squared, being equal to 2b squared. Let's see if we can't work something out here. Let's make it a little bit more simple. So we're going to have b squared being equal to 2k squared. We'll just divide both sides by 2. That means that, in this case, b is even, so that a, which we spoke about before, or sorry, b being even, or b squared being even, that means b must also be even. But we're going to have a bit of a contradiction. If a squared is even, it doesn't matter what the answer is going to be, or a also has to be even. You take 2, then 2 squared is 4, which is even. If we go 4, then 4 squared is 16, which is also even. It works both ways. If we've got b squared, then b is even. B squared also must be even. But that means that if I was to write a over b, then they're both even numbers, which means that they have a common factor in there, and they don't. So that means that root 2 has to be irrational. Because we've looked at it by contradiction. We've assumed at the start that root 2 is rational. So we've tried this part here to make it be rational. But it turns out that if a and b are even, then it can't work out. It's a contradiction. Hence by the name proof by contradiction. So that's all I'm going to really talk about in this video. The textbook does go through some stuff about logarithms, but because we haven't done those yet, we're going to skip over those for the moment. In the next video, I'm going to start to talk about imaginary numbers. So I do apologise that it's been a bit of a rambling, but I will go through another example in class of this, and we will talk a bit more about proofs as we continue on through this. Hopefully you guys have followed along. So if you've got any comments or feedback, just let me know. As always, thanks for watching, and we'll see you next time.